Okay. So next speaker is Cory Forsyth, and he's going to talk about image processing with Ruby.
Hello? Okay. Cool. All right. Can everybody hear me okay? The back? Cool. Okay. So the idea for this talk came last year. I was walking around the Museum of Modern Art in New York, and I saw an image that looked a lot like this. And then if you look at it closer, it looks like that. And I looked at this. Oh, did we lose it? Is it right? Okay. I looked at this, and I had a thought that I usually have in other parts. Is it going in and out? Okay. Okay. Nope. I can just shout.
Sí. Sí.
Cool. Okay. Yell at me if you can't hear me or something. So I was in the Museum of Modern Art, and I had a thought that I usually have in other parts of the museum, which was, I could do that. And this time it was a little different, though. I looked at this, I said, I could do that with code. And of course, since I love Ruby so much, I started thinking about how you might do something like this using a Ruby or a scripting language, and why you might want to do something like that. What sort of advantages you have when using a scripting or programming language that you don't really have in a GUI, something like Photoshop. So I basically kind of set off to try to figure out answers to these questions and just kind of hack around and see, how much I could do kind of purely through pixel manipulation using Ruby. So when you're working in an app like Photoshop, you basically have three layers. You've got your GUI at the top, that's your interface. In the middle, you've got the libraries and APIs, stuff that Adobe has written. And at the bottom, it's all just math, doing pixel value manipulations and derivatives and stuff like that. And you've got these hooks down from your GUI into the API, the commands on the menu and stuff like that. You can change the image in certain ways. And of course, it all just delegates it down to the math layer. And so in Ruby, on the other hand, you actually have kind of a similar setup. At the top, you've got your script that you've written. In the middle, you've got libraries, RMagick probably which is tightly coupled with ImageMagick. And at the bottom of it, it's all math again. And you've got the same sort of hooks from Ruby down to your libraries. You can change the image in certain ways, and again, it all delegates down to the math layer. But the big difference, and the reason why it's kind of exciting and interesting to do it this way, is in Ruby, you can, and this is the difference that you have versus a GUI, you can go straight down and manipulate stuff right at the pixel level, which you can't really do in an app like Photoshop or something like that. And so you get all this power and control, which is why we really write code in the first place, to be able to make it do what we want it to do. And so what I'm going to be talking about today is trying to make Ruby do Photoshop tricks. So it's worth taking a moment at the beginning to just kind of think about what sort of stuff is typically done with Ruby and image manipulation. On the web, there are two big things that come to mind. First, thumbnail generation and CAPTCHA generation. And they're really, like when I started thinking about this, there wasn't that much out there that I found that was different or more exciting than that. And I'm hoping by the end of this talk that you'll have some more exciting ideas of stuff that you could do with Ruby and images than I originally did. So there are four things I want to talk about. First, to give a little kind of intro and overview of RMagick for people who aren't familiar with it and how it works. And then there are a couple demos. I want to show how I made that photo mosaic, or how I made a photo mosaic like that one. And also image resizing technique, there we go, called seam carving. And then I want to talk a little bit about OpenCV, which is a really cool library that you can use to do face detection. It's a little bit of a departure from kind of pure Ruby pixel manipulation, but it's so cool that it's just worth showing. So all the stuff that I did today is with some code that I wrote that is basically just wrappers around different RMagick functions and to do math on pixels and stuff like that, and it's available on GitHub. So if you are interested and you have RMagick installed, you want to follow along, you can clone that repo. I'll be showing a lot of code samples and stuff, and wherever appropriate, I've also got like a link at the bottom of the slide so you can catch up later. Okay, so what is RMagick? It's a wrapper around ImageMagick API, which is a bunch of C code to do kind of image manipulation stuff. It's command line tools. You can use it to manipulate images at a pretty high level, changing contrast and blurring and rotations and things like that. But the important part for the purposes of this talk, at least, is you can also get, it gives you a couple different ways to get down to actually get the pixels out of the image, and you can then do interesting stuff with them and import the resulting changes to the pixels back in there. So you get that ability to do the raw pixel data. You can also use it to draw in images, which we'll touch on a little bit for some like annotation stuff. And you can't really mention RMagick without mentioning the fact that it's a huge memory leak, like a sieve, when you're creating your applications, stuff like that. So it's something you want to, for the stuff that I'm doing, it doesn't really matter that much because these are just scripts that fire off and then they release their memory at the end. But if you're using this in like a web application with something that is running all the time, it really gets exploded. And so you kind of have to be aware of that and figure out ways to work around it. So there are a couple important functions to know just to kind of stay on the same page here. In RMagick, you can load up a pixel object. It's got a constructor. Also gives you a constructor to load an image, the image list. It just loads an image into memory, and then you can use the different RMagick pixel iterators to get access to that data that you want. And there's also the draw object, which is used to draw on the image and change it and stuff like that. Okay, so an important thing to think about when thinking about all this stuff is that when you look at this image of Barcelona that I found on Flickr, we see the towers, the city, and the kind of relationships between the object. We process it visually a different way than the computer does. To the computer, it looks kind of like this. It's just arrays of data, numbers, and so when we manipulate images with code, we have to figure out ways of translating between what we see and what it sees. And so it's all the primary difficulty is figuring out how you translate that, and you've got to figure out ways to programmatically kind of explicitly change the pixels the way you want to without being able to see them, if that makes sense. And so that's kind of all that I'm going to be talking about today. So RMagick's got a couple different methods. It actually has a lot more methods even than I list here to get in and out pixel data, and I find them really confusing. Some of them return arrays of RGB tuples, some return arrays of pixel data, some return two-dimensional arrays, some return all the pixel data as a whole string. And looking at this, who knows what does what? What does image dispatch do? It does the same thing as image export pixels, but it's slower. So I don't know why it's there. Image view seems like a really useful function because it actually gives you a way to address the pixels directly, and so you can address them by the column and row values. But you should never use it because, for one thing, it's very slow. Here's some benchmarks just on a small image. The chart on the left shows functions from RMagick to get pixel data out of an image, and the chart on the right shows stuff to put changed pixel data back into an image. And these, I think your mileage may vary when doing your own code, but RMagick has so many different ways to kind of manipulate the image that it's worth benchmarking if you're concerned about the performance of any scripts that you're going to be writing. Okay, here's a quick overview of the code that's in that repo if anyone's cloning it or wants to follow along or play with it later. The most important part, it's got a little shell, bin RMagick sh, that just drops you into IRB, it loads up the libraries, loads up some convenience functions like IMG, which pulls in an image. So you can save some typing, and then you can kind of play around with all the stuff that's there just from the command line, which is kind of like it's fun. It's very Ruby-ish. It's a neat way to explore and kind of experiment. And then these are the pixel iterators that I wrote as wrappers over the RMagick stuff, which I think are more sensibly named and easier. They were a lot easier for me to use and understand. It should be clear, kind of like looking at them, what kind of values you're going to get back from each of those images. And they're just wrappers over RMagick stuff. Okay, so last thing about RMagick is the way you address an image in RMagick. This is pretty kind of fundamental and kind of simple stuff. That the origin is 0, 0 on the upper left. X values increase, X's or column width, however you want to call it, increases as you go to the right. Y or height or rows go down. And it's, like I said, simple stuff. But a good tip is if you're going to mess around with this stuff, start using, by using a rectangular image that has different values for the width and the height, because it turns out that they're very easy to kind of confuse in your code. And you'll have something that works really well with a square image, then you change it to a rectangular image, and the whole thing blows up, and you got to go back and find where you transpose those row and column values. In RMagick, the order of arguments is always column before row, too, so X before Y. And you just kind of have to get that ingrained into your head, and then it's very easy to use the functions. And I mentioned image view before. There are two good reasons not to use image view. The first is that it's slow, like I said, and the second is that for some reason in RMagick, it's the one exception to the column before row argument rule for RMagick. It switches the two up, and I find it just incredibly confusing and irritating. And so when I was doing this, I banished image view completely from my programming vocabulary. Luckily, it's kind of slow anyway, so there's no reason to use it. Okay, so let's talk about how to make a photo mosaic. All right, so this is the kind of the first step is you got to figure out how you translate what you see, into code. And so how is a photo mosaic actually created? And the way it works is you take an image. We're going to replace parts of that image, the smaller chunks of that image, with other images that closely match those chunks kind of in their brightness values. So we start by taking an image, and we'll superimpose a grid over it. There we go. And so now each of those chunks we're going to take, and we're going to find something else that we can replace that chunk with that closely matches that chunk in its kind of brightness. And then when you look at it and kind of pull back, it's going to resemble the original image. In this case, the chunks are large, so it's not really going to, we're going to have to make the chunks a lot smaller to eventually kind of get a good photo mosaic out of it. Okay, so if you're following along and have the repo cloned, this is the code. You drop into the RMagick shell and load up that image, and then there's a library called Photo Mosaicer, and you can create a new class of it, an instance of the class. You want to give it an image, and the first argument is the size of the kind of the grid size that you're going to chunk out. Lost it again. Chunk out your larger image to, and then the last argument is the size of those images that you're going to use to replace your new kind of pixels that you're going to be importing in and replacing with. And the important part of the code is that we're going to kind of go through the image, and this is just kind of looping through our larger image and breaking it up into those squares and summing up the intensity is the same as brightness. So we're summing up the intensity values for each of those squares, and that's how we kind of calculate what the brightnesses are of each of those chunks. And so when we do that to the image like this, it looks like this. First we're going to just look at grayscale images, and then later we're going to actually replace them with actual images that match it. Okay, so if you think of each grayscale block here as representing a pixel, a grayscale value pixel, we essentially just took our large image and turned it into a 10 by 8 pixel grayscale image. And so that's essentially kind of what a photo mosaic is, except we're gonna make it a much higher resolution, and instead of actual grayscale blocks, we'll use other pixels. So here are a bunch of pixels, or pictures rather, that I found on a Flickr Creative Commons search for Barcelona. These are gonna represent those kind of pixels, and that's our our color palette, or actually our grayscale palette. Their brightness values are the values that we can use later in the image to kind of replace. And like a typical 8-bit grayscale image has got 256 shades, so we want these pixels to kind of, the closer they match 256 levels of brightness, the better and less posterized the photo mosaic is going to be. Okay, cool. So this time the code is the same, except we specify for the photo mosaic object, we're going to specify a directory of thumbnails that it's going to use to generate, to swap out those files this time, or the chunks rather of the image. And the important part of the code I have up there is to we're just going to loop through all our thumbnail images, calculate their kind of brightness levels, the intensity, and all we need to do is we'll create a hash of them where the key is the brightness value and the value is the actual image. And then later, when we've taken our big image and chunked it up into those squares, we're just going to go through and find whichever image from our thumbnails is closest in brightness and replace it. So when you do that on the larger image, looks something like this. Oh, okay. And so you can see at this size, the individual details of those smaller images totally kind of wash out. The eye catches the smaller images, and you lose the bigger thing. So we're clearly going to have to increase the resolution by making those pixels smaller in order to actually see something. So if we do that and switch our chunk size down to 10 pixels, say, instead of 100, we get something that looks like this. So that is photomosaic, and it's just it's just like 4 lines of code from that repo. And if you zoom in, it looks like this. Keep going further. See? Oh, I'm going ahead of the transitions. Okay, and there it is, all the way zoomed in. And you can see that the chair is that's our brightest pixel from the source images, and it kind of like does posterize it a little bit. So this could have been improved even if we had had more shades of light at that higher end. Okay. Let's see. So, oh yeah, and this is what happens. I got ahead of myself. If when you are programming, you get this control, you can kind of do whatever you want, and especially loops with changing values. And so if you loop through the whole thing and incrementally increase the resolution each time, you get something that looks like that. I'm going to run it again just so you can see it. So, kind of cool effect. Okay. Now I want to talk about seam carving. Is anyone familiar with seam carving? The idea behind it? Cool. Okay, good. Well, this will be new for everyone then. Okay, so the idea with seam carving is that there are better ways to compress an image down, and I don't mean file size compression, but I mean actually like changing the width or the height of the image than just squeezing it, which is the typical kind of resize method. And if you're going to squeeze it down, it looks something like this, and you can see that as it goes down, the width of the towers kind of proportionally squeezes. Everything gets proportionally squeezed down, and you lose a lot of information. You end up with something where the sky is kind of proportionally squeezed down as are the towers. And the towers here are the really interesting things. We don't want to lose very much information about them when we do it. So that's where kind of seam carving comes in. It's also called content-aware image resizing, and it squeezes an image down, but it pulls out the parts of the image that don't have a lot of like information value or that are of kind of low information density. And so we're going to go through and kind of find the parts of the image that don't have that much information about them, like the sky, for instance, in the image, and pull those out preferentially first before we pull out like pieces of the tower. This is a lot easier to show with an actual image. It speaks. So this time we are carving seams, and basically what's happening is we're pulling out the sky, because the sky is not very interesting in this picture. We don't need a lot of information about the sky. And so you can see this time the towers are still there. The image is the same size, but the towers, except now it gets a little funny when it gets really small. But up until then, we had like this great image that kind of had all the important stuff of the original image and was half the size. And that's what seam carving is all about. Okay, so like I said kind of at the beginning, the idea is that you got to figure out how to talk to the computer, translate things from kind of the visual into the programmatic or the algorithmic. And so we have to figure out a way of telling kind of figuring out what parts of that image are the low information parts. And the way we do that here, I think you could figure out a lot of different ways to do that, but the way you do it in seam carving is you find the edges of the image and you find places that don't have a lot of edge information, and you call those the low information places. And so you kind of pull those out. So this is kind of how we do the edge detection. There's a method called using the Pruitt operator, which is it's just a matrix of values that you apply to each pixel as you go through the image. Like this is what it looks like. So say we're trying to find the edge value of that pixel there that's outlined in red. We'll apply this Pruitt operator to it. Essentially, like this may look familiar to you from algebra. We're taking the the derivative. We want to see how much the information is changing over time. So actually, when we do edges, we always shut it down to grayscale, because we only really care about brightness values that are changing. And so here, we're just going to multiply that pixel kind of by this matrix, which essentially means we're going to sum up the three columns on the right, rows on the right rather, that have the ones, and subtract the three values on the left that have the minus ones. And that's going to be kind of like the amount of change in the x direction. And the Pruitt operator, this one, is, I mean, it's kind of arbitrary here. There are other matrices that you could use that are like kind of bigger and take into account more information around the individual pixel, but this one is simple, and it works reasonably well, and it's pretty fast to compute, so that's what we're using. In the y direction, it looks like same thing. We're subtracting the value, so we're just looking how much it's changing as it goes downwards this time, instead of across. This is the code to do it. So for each pixel, we kind of like loop around it, and we sum up the pixel values around it. That x mask and y mask are just, that's a function that figures out basically what part of the Pruitt operator we're at that spot. So if you do that in the x direction, this is what it looks like. There's the edges. You can see in the sky, for instance, that everything is very kind of like vertical, because we're only looking really now for changes that are going across the x direction. And if you compare to the y direction, everything is very kind of horizontal, all the edges, because we're looking at things that are changing as you go down. And when you put them together, those are your edges. That's the edge. And so we're going to use that to kind of figure out the interestingness of each point of the image. And an interesting side note is that you can actually, if you take the x and the y magnitudes and you take like the sine or the cosine or something, you divide them, you take that ratio, you can actually figure out what the direction of that edge is. Exactly. And so sometimes you see in software like colorized edge maps, and the way they do that is they're figuring out the direction at each point of the edge. It's kind of cool. That's how that's done. Okay, so now that we've got the edges, we want to figure out how we want to figure out kind of like which seams down the image are the non-interesting ones that we can kind of pull out of it. And the way we do that is we take an energy map of the whole image. So this is actually best explained with a picture. So now assume this is our edge values instead of the original image, and the value of the edge at that red pixel is 5, and above it, those are the values for the ones above it. And so we want to figure out what's the cheapest way to get down to that 5 pixel from the top. And the cheapest way is going to be to go through that 3 down to the 5, and the value, if you go that direction, is 8. And so the way we calculate this energy map is we're going to go through each pixel in the whole image of the edge image and calculate that cheapest path down from the top to it. And we just kind of like dynamically do that row by row, calculating the values from the row above it. Okay, so yeah, we're going to repeat that process for every pixel in the row. Here's the code that does that. You can ignore the first two parts. Those are edge cases, literally, where we do the sides, and then the bottom part is kind of where the real code is. And all we're doing is really just going through the row. We're figuring out the minimum value of the 3 columns in the row above it. We just really care about the kind of like the connected path down to it, and we're summing that up, and we loop through the whole image, doing that across every row. Okay, so putting this all together, this is what we have. We've got the original image. Here's its edges. And then if we take that energy map and normalize all the values, it looks something like this. So you can see like everywhere in that image, the amount of brightness it is kind of how costly it is to get down to the top, from the top down to that pixel, in like how many edges you have to go through. So you can see like the base of the towers, it's very bright because you got to go through a lot of tower edge to get down there. Okay, so now that we've got the energy map, what do we do with it? How do we actually find that seam? And the answer there is that we want to start from the bottom this time, because every pixel at the bottom is a total sum of the cheapest value from the top. And so we're going to start from the bottom and work our way up. At each row, or the bottom row rather, the lowest value is going to be the cheapest path down there. and then we just go one row up and find the next cheapest value above it that's connected to it, and then we kind of keep working our way up and up and up. And so this time the code looks like this. Yeah, so again, edge case is at the top. The bottom is the ideal case where there are 3 pixels above it. And so we're going from each row, we're finding the index of the minimum value of just those 3 above it, because we want to make sure that everything's connected. And then we're going to kind of build up an array of those values, and that's going to be the seam that we are going to carve later. So if you've got the code cloned, the repo cloned, this code will find that seam. It's just going to be an array of integer values. Okay, so that's it. That's our seam. So it found the cheapest value, and then we're just following it up kind of at the top, taking the shortest path from 1 to the 3 above it every time. And that's what it looks like superimposed over the edges. And on the original image, that is our, if you can kind of see it, that is our cheapest path, the original seam. So if we take that out, we've taken out kind of like the least interesting part of the image, and then we just have to do that one time for every pixel we want to shrink it. Yeah, that's all the code does. And here you can see kind of like a side-by-side comparison. The carved image has much more information kind of than the resized. So that's it's a kind of really interesting technique to do. And there are other kind of cool things you can do with it, is because you can actually influence the okay, so you can actually influence the edges if you want, and oh, here it is. Okay, so you can see the seams, kind of every time. That's where they're coming from. They get a little bit kind of fuzzed out. Okay, but another thing is you can actually influence the way the image gets compressed, because you can change the edge values. If you change that kind of edge map, it's going to change the way the image gets shrunk. So for instance, you've got it like this. This is the only part of this whole talk that I did in Photoshop, is right there. I just erased that from the edge map. And then if you use that, you are going to actually kind of preferentially, so we've basically said now that's the least interesting part of this image, that black splotch on the edges. And so if you use that to kind of build your seam, to do the seam carving, you can kind of preferentially erase parts of an image, which is kind of cool. And it does it in generally a pretty seamless way. You kind of can see a little bit of an edge there, but it basically just erased that smaller tower, which is kind of cool. Cool. Okay. So now on to face detection with OpenCV. So I don't know how many people have installed RMagick on their machines, but it's kind of a pain to install. It's got a lot of dependencies and stuff like that, and you've seen nothing. If RMagick had trouble, you've seen nothing yet until you tried OpenCV. That thing is a real pain to install. And I get the there is luckily a Ruby gem for it. You've got to install the libraries yourself, but then there's a Ruby gem that gives us a way to kind of get into them. I have a fork of it that has some fixes and some kind of detailed instructions on how to get OpenCV installed. It's worth installing, because once you get it installed, it's very easy to do really cool stuff like face detection and stuff like that. I get the impression from when I was looking at this code that it isn't used very often on the Mac, because actually in one of the C files for OpenCV, the function that gives you a handle to a carbon window, which is what you would use on Mac, is hard-coded to return null. So you actually, in order to get it to compile and use carbon windows on a Mac, you actually have to go in and change the C code. So get the impression it's not used that often on a Mac. But it doesn't mean there's no reason you couldn't. Okay, so here's a kind of like a one-slide crash course in the way face detection works. The most common method is using something called a HAR cascade. HAR is the name for a certain kind of feature that is basically, it's just like a binary kind of black and white feature, something very simple that looks like that. And the way it works is you have to take a bunch of these HAR features that look like little black and white squares, and you apply them to different parts of the image and see how closely they match in each of those spots of the image. And then you have these classifiers that do that a bunch of times for a bunch of these different features, and it's called a cascade. And as it turns out, if you do enough of these, they kind of have they boost each other, and you end up getting a really good idea of whether or not there's a face there. And the way you do that is you've got to train the system. And the way you train a hard cascade is you find thousands of images of faces, and you put them against different backgrounds, and then you tell it, the computer whether it is or is not a face. And here's one place to find faces if you want to do this. There are a bunch of face databases online. This is from the Yale face database. This is like subject number 12 or something like that. There are all these like CS departments have these databases of faces, and you can use, and they've used to kind of train these classifiers. But luckily, you don't have to do any of that, because OpenCV has a bunch of trained classifiers for you. It's got like 2 frontal faces and 2 side faces. The detectors aren't very good at figuring out like using the same detector to find faces in different orientations. So you can either kind of look for faces head-on or on the side. And okay, so here's how you use the code to actually do this in Ruby. So you need to include this OpenCV gem, and then that first line is just going to open up an image using OpenCV. You're going to load it up, and the second line is RM image is our RMagick image, and that's just there so we can draw on it afterwards. And then the detector is an OpenCV CV hard classifier cascade detector, and you just load it. They're all XML files, and a bunch of them come with OpenCV. So the frontal face means it's going to look for faces dead on. And then you just call the detect objects method on your image, and it's going to yield a bunch of basically rectangles that it thinks are including faces. And it's really simple to use. And then this code, the draw, the new draw object is we're basically just going to draw that red rectangle on top of the image. That's why we have the RMagick image object around. Yeah, so Jennifer Aniston, she has a very detectable face, apparently. OpenCV, I know they say humans, we prefer faces that are like very symmetrical, and I think OpenCV is the same. It's a lot easier for it to find, but it actually works really well on any sort of face. Anyway, so there's hers, perfectly matched on top of the face. And I know a crowd like this can kind of come up with a bunch of better ideas or kind of more noble uses for this than I did, which was this method. It's included in the repo called the put a funny hat on a celebrity method. And this just basically does the same thing if you look through this code as the code snippet that I showed you before, except this time instead of drawing that rectangle, we're going to resize a little hat to match the shape, the size of the face, and kind of move it up a little bit to the left, so it looks like it's actually on top of the head. And so if you do that, if you take a video from an interview on CNN and you run this code against every frame and then restitch it back together into a video, you're going to get something like this: the leader of Iran giving a press conference while wearing a hat. I watch the lower right. Every time his like little face appears, it's got the hat on it. I like that. You can see when he turns his head, it's no longer frontal face. The hat disappears, actually. Yeah. So that's how you put a funny hat on a celebrity using Ruby and OpenCV. Thanks a lot for listening. I've got the code up on GitHub, and for the gem for OpenCV, also the Image Labs repository, and then this delicious link has a bunch of kind of links that I found for research while doing this, and they're all tagged up if you want to follow along with any of this stuff. So thank you very much. Anybody have any questions? Oh, way at the back. Yeah. Sure. Yeah. Could you please repeat the question? Yep. The question was how, on a very basic level, how does the hard cascade classifier work? The short answer is I don't really know. Luckily OpenCV kind of does that for you. But basically, I mean, it is just a bunch of really simple classifiers, things that kind of like overlay the image on top. Okay, I thought maybe there were Twitter streams behind me. It's just a bunch of really simple classifiers that check for like little things like I showed you, those like white and black squares, and kind of check, and they're all binary too. It's like, does this look kind of like this? Does it pass the threshold for this thing or not? And you just, I don't know how many of them you have to kind of do in a row, but eventually you get to the point where it says yes or no, this is a face object. And it does something, it creates something called, like, I think, an integrated image, which is it pre-processes the image, so it kind of knows, actually I'm not exactly sure how it works, but it allows you to do it at different kind of levels throughout the image at once, which is kind of cool. Otherwise it would be very kind of tedious if you had to compare different rectangle sizes across the whole image at every spot. So, any other questions? Yeah. Okay, so the question was how far can it go? Can you see whether faces are similar and stuff like that? Yeah, this is only going to say yes or no, it's a face. It only works for human faces too. Someone asked me once whether it would work for a cat's face, and the answer is, I tried. The answer is no. Yeah, what you're talking about, I think, is face recognition and stuff like that. And so I don't know if there are any libraries for Ruby that do this. I don't think there are that actually do the recognition to tell whether a face is the same as another one. But this would give you a pretty good start. Is you could find the faces, and then you could do something like skin tones and stuff like that, and you would kind of compare the characteristics of the color profile, for instance, of that image, stuff like that. I mean, I think that's how you would start doing something like that. And any others? Are there methods available? So yeah, the question was, are there methods available for training classifiers? Yes. OpenCV comes with, it's a bunch of C programs that you can just run on the command line. They're pretty complicated because you've got to give it a lot of different cases. You have to give positive and negative, and you have to give it in different orientations and on different backgrounds and stuff like that. So generating the thousands of images that you would need to train it is the tedious part, but there are command line tools that you can use to generate your own classifiers. So if you wanted, like that one guy, to find cats' faces, you just need to find a bunch of cat faces and make your classifier. It'll do it. Yeah, it can match any. It doesn't have to be faces. It can be any sort of object you want to detect. Nope. Yep. Yeah. It can find multiple faces in a picture at different sizes and stuff like that. Yep. Probably not. The question was, what about performance? That's a great question. And I was joking with someone that, the answer to the question of this talk, who needs Photoshop? The impatient people. And if you're patient and have the time, use Ruby. It's definitely not as fast as I'm sure it would be if it were in C straight up, or using other kind of specialized tools. So for the most part, this stuff is not real time. But the face detection, actually, because it's just using C libraries, it's just binding to C, or it's a gem that wraps around C code. It's pretty fast. It's not quite real time, but maybe like for each of those images, it'll find it in maybe 100, 200 milliseconds or something like that. So to encode that video, for instance, took like maybe 3 or 4 times the length of the video. Not that long. Yeah, it's close. Okay, thank you very much.